Hey everyone, it's Ross. I'd like to give you a video demonstration of sort of the to scale model of the setup for the first way to handle sound interference in a simple manner or straightforward manner. So here I have two speakers facing each other. They're lined up. I have a string and some, excuse me, a tape measure for reference. This is typically too short. In the sort of 40 centimeter range. You really do want to be about 1 meter apart for this to work really well. So keep that in mind. So the idea here is that you set up two speakers that are going to play the exact same sound in phase. That means there's no delay. There's no sort of offset between in the signals they play or the way they're playing them. So typically what you want to do is you want to play a pure tone. So for those of you who don't know, a pure tone is like a nice single note. So, if you're doing, I think it's like a 3, let me double check real fast. So if you want like a mid G or a G4, you would have a note that's about 392 hertz. And then if you want a high E, you'd play something that's about 660 hertz. They're a little lower than the 392 and the 660, but you'll get pretty close. And notes usually sound a little bit better if they're just a tiny bit sharp. So hey, there you go. So you get a tone generator, or you get a clip recording. Usually you want the tone generator so you get like pure signal through, but you do what you can. And so the idea here is that you pick a set of frequencies, you set your speakers a distance apart, you go ahead and turn it on. And then what you do is you get a microphone, your sensor, and what you do with that microphone is you move it between the two speakers all along that center line, and you look for spots where you get a high to a low. And so the idea here is that, last week we had a standing wave on strings, so you had the reflection, you had a single source and then it reflected, and you got yourself an interference of standing waves. Here, because you're playing that single tone, and they're facing each other, you're going to get interference purely because you have oncoming waves, right? So like, you have two waves, they kind of go up and down. So as they travel, they'll sort of overlap in a certain way. And in this case, you should get really good highs and really good lows, where you get constructive and destructive, not pure, it'll be a mix. Okay, so the goal here is you choose your lowest frequency. So maybe it's middle G, maybe it's a little lower, maybe like a low A, I don't know. And then, you pick a few other ones. Maybe pick middle A, maybe pick middle D, maybe you pick high G, high E, whatever. You pick however many you want. And you play the tones, and you go ahead and you measure, and you say how many highs and lows did I find, right? So you take so many in your meter. And then you could say, what's the distance between those highs and lows? So as you do that, you can sort of sketch out the wave and the overlapping waves. And then you can think about, if there's a higher frequency means you're oscillating more times. You should sort of get more overlap, and you should get more highs and lows. Another way to think about that is that if you have a higher frequency, you have a lower wavelength. And so if you have a lower wavelength, you should be able to fit. If you have a smaller wavelength, you should be able to fit more wave patterns, waveforms, and so you should be able to have more nodes and more cancellation. Or if you have a low frequency, that means you have a high wavelength. And so if you have a high wavelength, small wavelength, and you have a high wavelength, well, you're going to get a lot less cancellations in there because you can't have as many overlaps, let's say. So this is the first way to do simple wave interference with sound. You get two speakers, you choose your tones. For every tone, you measure where your highs and your lows are. You get the distances between them. And from those distances, you can estimate the wavelength for that tone. And then based on wave speed theory, you can say, okay, we know the speed of sound pretty well. I know which frequency I chose. So then you can get a theoretical prediction for your wavelengths. You can compare them. So that's one way to compare theory to experiment, sort of how people figured all this stuff out. And then another thing you can think about is, you know, what sort of patterns do you see for low frequency to high frequency? You know, what sort of patterns do you observe? I already mentioned one. So hopefully this and the video to come about the second way, and then I'm planning on uploading a mini lesson. So if you haven't seen that yet, go check it out. All right, everyone. Thanks. Have a good one.